Okay, thank you everyone for coming to my talk. Today I will be talking about large language model agents for quality assurance. And in this talk, I want to focus on two things. First of all, of course, to just showcase the potential for large language models and how we can use them for games. And then to also counteract somewhat the hype around large language models. So to actually showcase what are the limitations, what can they do and what can't they do well. So my name is Dominik Jörsen. That's me with a little bit more hair than before, than now. And I'm a PhD student at the Queen Mary University of London, where I'm part of the Game AI group to research AI for games. How can we develop AI that plays games? How can we develop AI tools for game developers? A lot of different things. And my PhD is partially funded by IGI, which is the EPSRC Center for Doctorate Training in Intelligent Games and in Game Intelligence, which is a program for PhD students to essentially research game AI or general AI for games. And I'm only partially funded by IGI, because the other partial funding is coming from Creative Assembly, where we are trying to look into playtesting complex strategy games, such as the Total War series developed by Creative Assembly. Now, today we won't be talking about Total War in specific. It will be more about quality assurance with large language model agents. We won't be looking at Total War, but of course my goal is to actually develop something that works for Total War. And I split this talk into three parts, roughly three parts, which is, first let's talk about why should we actually care about large language model agents for quality assurance. And then, of course, how can we actually apply them to our games, create like an agent that maybe plays games using large language model agents. And finally, analyze those agents, see what they can do well, what they can't do well, and come up with some tips and tricks for game developers or game quality assurance people to look at, to better use those agents. So let's look at large language model agents for quality assurance and why should we care. And before we actually want to discuss why should we care, maybe let's discuss quickly what are large language model agents or large language models. And it's quite simple. So we have language models, which simply are machine learning models that predict text, meaning we give them as input some piece of text, and their goal is to just predict what is the most likely way to continue the piece of text we've just given to the language model. And then, as the name implies, large language models are just larger language models, or LLMs, as I like to call them, which both have a much larger machine learning model that was used to train on data, and we used a massive amount of data, usually from internet, like a lot of internet data, a lot of data that we can scrape from everywhere. And because they were trained on so much data, they usually have to implicitly somewhat learn a lot of different things, right? If you learn a lot about different pieces of text, we have to do a lot of different tasks implicitly, such as doing math. If we have a piece of text that asks you what is 1 + 1, then the language model, of course, will say the most likely way to continue this text is to say the answer is 2, and not something weird like the capital of Belgium is Berlin. And that's the basic idea behind language models. They just simply predict text, but because they were trained on so much data, it looks like they're actually doing a lot of different things that are very smart, which we can then use. And let's look at one example, such as where I asked a large language model, in this case, ChatGPT, which uses in the background language models, to write a function for computing the Fibonacci sequence in Python. And the code in itself doesn't matter that much. I tested this code, it works exactly how I wanted it to work, and it works perfectly. So we can use large language models to just program for us, which is already quite impressive, in my opinion. And they have some very nice property, which I usually say context is memory, where in this case, I'm asking the language model to compute a simple formula where the answer is 1, which it computes correctly. And then I'm just asking it, okay, what if we now add 3 to the previous result, which was 1, and then it answers 1 + 3 is 4. And what's interesting about this is technically the large language model seems to have remembered what we just talked about, but in reality what ChatGPT is just doing is taking the entire conversation that we just had with the language model, it passes it back into the large language model so it can analyze the entire conversation so that it then knows, oh, the previous answer was 1, so I can just add 3 to that. So it doesn't really remember, so I just call it, given context, it can memorize different things. And this can be quite powerful for us if we want to create language models for games. Of course, they're not perfect. Let's look at counterexamples such as hallucinations, which probably a lot of you are aware of, where we ask the large language model something, it comes up with random things that we don't know about. In this case, I asked it, who is Dominic Jurgensen, which is me. And it told me I'm a professional wrestler from Belgium, which I wasn't aware of. And I've checked that name, and certainly a person, Dominic Jurgensen, which is a professional wrestler from Belgium, doesn't exist. So I asked it multiple times, who is Dominic Jurgensen? And then it told me I'm a Belgian entrepreneur. I'm not sure what it has with Belgium, but then it told me I'm a Belgian entrepreneur. Finally told me I'm not a widely recognized figure, which I found was kind of rude, but might be fair. And finally it told me I'm a Dutch professional footballer. Yeah, none of those people exist. And the reason for this is large language models simply predict text. They don't care about how something is true. As long as something looks like it could continue the piece of text that we've given it, it's just gonna spread out whatever it thinks it might seem correct. So now that we've run somewhat good understanding of large language models, let's look one application for games. And this is one of the paper that that essentially inspired my entire research, which is called Generative Agents. And in this paper, the researchers actually tried to simulate an entire town of NPCs using only language models, meaning NPCs have a schedule where they interact with the world over an entire day. And this entire schedule that they have is generated by one language model that defines how every NPC has to act based on a certain, based on how the agent should react, like based on its theme. NPCs can talk with each other. And again, the dialogues between NPCs are generated by language models, and dialogues are also usually remembered by NPCs. Finally, we have states in the environment, such as an oven maybe, that we can turn on or off. And the state is just represented using a string. And again, a language model is just used to define when an NPC interacts with an object in the world, it's going to change the state of the objects in the world. So everything is simulated using NPCs, which is quite impressive. And then the authors looked at, okay, we're going to ask one of those NPCs to hold a party, which was the entire prompt that was given to one of the NPCs. And there can be a lot that can now go wrong, right? The NPC has to tell all the other people that he wants to invite them. The people that are invited have to remember that they actually were invited. They have to actually go to the party on the correct day at the correct time. And yeah, a lot of things that can go wrong. But in the end, what happened is, the NPC actually managed to invite all the people, and they gathered in this room and had a small little party and had some fun together. Of course, this is not really playtesting. This is just an agent simulation using large language models, which in itself is quite interesting. But let's look at how we can actually, playtest or quality assure, make sure that our game is on a good quality. So large language models for quality assurance. And maybe first, let's address the elephant in the room. Will large language model agents replace quality assurance? I think that's extremely unlikely. And let's talk about that. So large language models are mostly suited for straightforward tasks. That's what I've gathered so far from my interaction with large language models, meaning if we have some kind of repetitive task where a human would just go through the motions, not even think about it, that's what large language models can do very well. They are very bad at thinking outside of the box, thinking creatively. And usually when we think about quality assurance, we want to do a lot of things. We don't just want to check that our game is bug-free. We want to make sure that the game is actually fun, that it's intuitive, easy to play, a lot of criteria. And large language models are not very well suited for creative tasks. They're well suited for essentially optimizing or automating the more repetitive things. And that's why I'm currently, on this talk, I will be looking at just play testing, meaning we want to check, is our game bug-free, which is the best kind of thing that we can do with large language models, even though we even have to restrict this kind of use case. And let's look one simple example, which is we have just one simple agent. We have a mouse, a key, and a chest, and we want to check, okay, can we actually open the key can we open the chest using the key? And there are a lot of ways we can playtest this. And the easiest one is, of course, when we have a developer that just playtests the game as he develops the game, he can just pick up the key and open the chest and then check if everything works correctly. Of course, as time goes on and we change our game, we have to keep testing if this actually works, which can be extremely expensive and in general very tedious to keep repeating. So it might be tempting to try to automate this using maybe some kind of agent that we implement ourselves, where we essentially implement whatever the game developer just tried to do, and let us run every time we want to check if the game still works, which is nice. But of course, this has some problems, like implementing these agents can be extremely difficult, especially if our game gets very complex. And of course, if our game essentially evolves over time, then it's very likely that it's going to break again, and we have to again tediously try to adapt the code to actually make it work. So this might also not be the optimal solution. It might also be tempting to do machine learning, where we maybe ask the machine learning agent to somehow test our game so that it's somehow bug-free. First question would be, well, how do we actually define how to playtest our game? And the second thing is, machine learning agents usually see the game as a black box. They don't see a key, they don't see a chest. They just do everything randomly until they probably crash into a wall and maybe get stuck somewhere else. So technically, this could be quite nice for testing a lot of edge cases, a lot of brute force testing approaches. And as the agent evolves, it might even be able to test our game in a much more sophisticated way. But again, as the game evolves, machine learning agents have the tendency to just overfit on whatever we've trained it on. And then if we add new features to the game, they're again going to break. And so we have to retrain them, which again is going to be very expensive and time consuming to do. So what I'm now proposing is a more hybrid approach, where we have a large language model and we give it some kind of task that we want to test, such as pick up the key and use it to open the chest. And then the hybrid approach is where we give it access to a bunch of tools that we usually have as developers that we already need for developing the game, such as pathfinding, moving to certain places in the world, picking up objects, or in this case, opening chests. And so the large language model is going to use those tools that we provide to it to playtest our game. So in other words, the large language model is not doing the low-level planning, like moving the agent one by one by one. Instead, it's just doing the high-level planning, which is best suited for, right? Large language models know there's a key, there's a chest, I can just pick it up and open the chest, which they are best suited for. But they're very not well suited for just moving one by one, especially since they cannot see the map very well, unless we use some kind of multimodal LLM that can actually see images. So this is the kind of approach that I'm trying to now sell to you. And let's look at one example of how this could look like. I now want to talk about one particular agent, which is called Voyager. That's an agent designed for the game Minecraft, where we have a large language model which we can give tasks, and it then is going to play Minecraft using that task to actually solve that task. And it's very complex on how it actually does that. There are a lot of bells and whistles, but what we want to focus on is just this simple example where the large language model generates code to actually solve the task, meaning we give it some kind of task and the language model generates code that then plays the game for us. So it essentially implements the agents for us instead of us having to write some code ourselves. And how this can look like is, in this case, we ask the language model to gather some cactus. And if we let this run, we can see how it seeks out cactus, mines it, and then picks up the items. And again, then it walks to another cactus, picks it up, tries to somehow punch the ground randomly. And finally, it finds some more cactus and picks it up. So this works nicely. And it can, of course, do more because we have a language model. We can just give it more tasks, such as fighting an Enderman. If you don't know what an Enderman in Minecraft is, it's this black creature, Slenderman creature-like. And essentially to fight it, we have to hit it. So the LLM generated some code that goes to the Enderman and keeps hitting it. And it keeps hitting it with a shovel, which is not very efficient. But at least it works. And eventually it manages to kill the Enderman. So that also works. So we have some kind of code that fights Enderman for us. And we didn't have to do more than just ask the language model to do this for us. And this is for one example of how such code could look like, where we ask the language model to craft some wooden planks. And wooden planks in Minecraft can be created by first mining some logs from a tree and then turning it into logs, into planks. So the first thing the language model is doing, it's just checking if it actually has some kind of log in its inventory. If there are no logs in its inventory, it's first going to gather them. And finally, once it gathered some logs, it's going to turn them into planks, which can be done using the crafting bench in the player's inventory. So this is all nice, but of course, how can we actually apply this to our games? Because in most cases, we don't have access to some kind of pro-game API that we can give the language model access to. And a lot of games are usually not that easily predictable, where we can exactly say, like, this code is always going to do the same thing. What if something unexpected happens in the game and you need to reactivate that immediately? So for that, I want to look at my own code, and I'm at my own research example, which is called NetPlay. Language model agent for the game NetHack. And while I will be looking at this one simple example of NetPlay, most large language model powered agents work in an extremely similar way. So if you know how NetPlay works, it's very likely that you also can extend this to any game that you want to apply this to. So let's maybe quickly talk about what is NetHack. Now this is the ASCII view. I will have a little bit simpler view in the future, but NetHack is a very old roguelike or dungeon crawler, where we have a lot of different items and monsters, meaning all the monsters in this game have all different strategies on how you have to defeat them. And there are a lot of different items that have a lot of different purposes and hidden applications. So it's a very complex game. Not only is it complex, it's very difficult. There are up to 50 levels that you have to traverse to actually get to the final level, pick up an item, and then go back to the first level to unlock the 4 final challenges, where you have to do a lot of different things to actually survive. Most maps in NetHack are split into rooms and corridors, which is not super important, but it's going to be a little bit relevant when we want to apply it to a large language model. Of course, because it's a roguelike, we also have stats such as strength or agility. And NetHack also generates game messages, which usually tell you what is happening in the game, which is quite convenient if you want to apply it to language models. Now, why I've chosen this game is quite simple. This game is extremely complex and difficult. And most language model agents usually just show you, oh, this works and it's fine. So I've chosen this game because it's so extremely difficult to just figure out what are the limitations of language models, and where do they fail, and what can they actually do well. And let's look at an example of how this language model agent actually plays. So we have a fountain and we have our player with an orange cat nearby. And I'm now going to ask the agent to just drink from the fountain. So I'm just writing in the chat, please drink from the fountain. Now it's thinking. And then it finally decides, okay, to actually drink from the fountain, I first have to walk to the fountain, which it then does. And the next thing it's of course going to do is it's going to use the drink action. And finally, this prompts the game to ask you, are you actually sure you want to drink from the fountain, which can be very dangerous, usually in this game. But in this case, it succeeds, and we drank from the fountain, and it works. Perfect. Sorry about the pop-up. I'm not sure why that happened. So, and finally, the language model actually told us, okay, I've drunken from the fountain, and it has now dried up. So not only did it drink from the fountain, it also told us, I'm done with the task, which is very nice to have. So it works quite nicely. But how does it actually work? So let's look at the architecture of NetPlay. And the first thing we want to do is describe NetHack to the agent itself, right? Some kind of observation description where we tell the agent, this is what you're playing, this is how it looks like, and this is what you have access to. We're going to look into this in a little bit more detail in a few seconds. To also play the game, we have to give it some kind of task and a set of skills or tools in this case, right? If you remember back, we give it access to some kind of tools so that it can play the game in a high-level manner, meaning the language model doesn't have to do low-level planning. It just gets access to our tools that it can use to play the game in a more efficient way. Once we have essentially an observation description and some kind of set of skills, we can just construct a prompt that we give to a large language model, which then outputs some kind of JSON where it tells us what it wants to do. In this case, it told us, I want to use the move to skill and move to the x coordinate 48 and y coordinate 11. And finally, we can just run the skill and play NetHack using the skill. And once the skill is done, we just reprompt the LLM with whatever we are, which state we are in at the moment. Now this works, but LLMs are not the smartest, so they might make a lot of mistakes. They might plan wrong, or they might make a silly mistake or something unexpected happens. So most language model agents also have a third component, which is some kind of feedback loop, where the language model receives feedback from whatever it has done before, so it can react or replan to correct itself. Now that can be done in a lot of different ways, but the way I've done it now is by using some kind of memory system, where I keep track of a lot of different things that happen in the game, like what did the LLM try to do, like its own thoughts, I'm going to put them back into the memory. The game messages generated by Netic, I'm also going to put them back into the memory. I'm telling it which task it has received, and yeah, a lot of different things. So it can just analyze the memory and use that memory to plan better in the future. And this is the entire architecture of how most LLM agents work. We have observation descriptions, we have tasks and skills, and then we have some kind of feedback loop. Now for Netic, I had to do one more thing, which is in Netic, it can often happen that you suddenly a monster appears and you have to react to it immediately. And if you don't do that, they are just going to attack you and kill you. And my skills don't react to that themselves. The language model should do that. So to handle this, I have one more thing, which is a tracker, which keeps track of, does something unexpected happen in the game, such as a monster suddenly shows up. And if that happens, I'm going to interrupt the skill execution and just reprompt the LLM so it can immediately react to whatever situation we are in. And that's roughly the entire architecture of NetPlay. So let's look at it in a little bit more detail. Observation descriptions. Now, this can be a very tricky part depending on how complex your game is. For NetHack, there are a lot of parts that are easy to describe, such as a general information, right? You're playing NetHack, you're at this position, and maybe some tips on how to play. Then, of course, NetHack generates game messages, which is very convenient. So we can just give the game messages to the LLM as input. We have stats, so we describe the stats to the large language model. And we have an inventory where we have a lot of different items that the language model has access to. So we also describe the inventory, which is also, again, just text. And this brings us to the actual difficult part, which is the map. How do we describe a map to a large language model? That's not very easy unless we have, again, access to a multimodal LLM that can actually understand images. I tried to use one of those multimodal LLMs. Sadly, they've been mostly trained on real-world data, so they don't really understand these more abstract representations. Even if we use a more sprite-based view instead of ASCII, they have a lot of trouble to fully understand what is happening in the game. So in this case, I've decided we're going to split the map into rooms and corridors because it's mostly rooms and corridors, and I'm going to assign a unique ID to every rooms and corridor itself. And then the large language model just gets its input. Oh yeah, maybe you're in room 3 at the moment and it contains these items, right? You're in room 3 and it contains a sword at this position and you can reach it in this many steps. And this abstracts away a lot of the complexity of the map. And it doesn't fully capture the complexity of the map, of course, but it at least allows the LLM to think in a little bit more sophisticated manner about where am I, where do I need to go, and how do I get there. Of course, it's not perfect, but this was just one test case, right? Can we actually get this to work, and how well does it work? The next thing I want, of course, to talk about is skills, right? The skills that we give access to the large language model so it can actually play the game in a more high-level manner. So what I'm now going to show you is not the language model playing the game, but it's me playing the game using the skills I've just implemented for the game. And the first skill I'm going to show you is actually the explore level skill, which is the most complex skill I had to implement, which is literally, as the name says, it explores the level. It searches for hidden corridors, which are very plenty in NetHack. It opens doors, and it just tries to fully explore a level until something, again, unexpected happens and we might get interrupted, which exactly happens now because we found an item, so my skill got interrupted. So now I'm telling it, okay, please pick up the item that we just found. And then, of course, we're going to get there and try to pick it up. And now an interesting edge case happens where suddenly a menu shows up because it asks me, there are 2 items at this place. Which item do you actually want to pick up? Now, technically, I could have changed my pickup skill to actually handle this menu. But what I've instead said is, if something unexpected happens, like a menu shows up, my pickup skill is just done. And we now have to manually handle this. So I'm going to use the press key skill, where I use keys to actually navigate the menu and actually pick up the item that I want, which is a dwarven corpse. I'm not sure why I want that, but I picked it up and I'm done. So I used 3 skills: my explore level skill, my pickup skill, and finally I navigated the menu by pressing keys manually. And let's talk a little bit more about skills. So these are some skills that I've implemented for NetHack. And there are a lot of design decisions that are quite important to make good skills for large language models, such as we should keep them as general as possible. Language models have the tendency to not fully understand what they're doing. So if you make very specialized skills, it's very likely that there's a very special situation where the language model makes a mistake and you try to make a skill that allows it to better handle the situation. That's not going to happen. In most cases, it's probably going to ignore this special skill, except in a situation where you don't actually want it to use it. So try to make skills that it can just use in a very general sense to do a lot of different things in the game. As I've just mentioned earlier, the pickup skill doesn't actually handle menus or anything else. Instead, the moment an edge case happens, I don't have to handle that. I can just say, if my skill somehow gets in a situation that I cannot handle, just let the language model handle it, because that's why we're using it, because it has so much knowledge. It should be able to handle all the edge cases for us. And finally, we should make the skills intuitive. Now, this is quite interesting. Let's assume the pickup skill doesn't have an X and Y coordinate as input, meaning you just pick up whatever is currently below your character. The problem is, in this case, what the language model has tried to do, in my case, to just assume that the pickup skill has an X and Y coordinate, and it's just gonna hallucinate that it's most intuitive if pickup has an XY coordinate, so I'm just gonna pretend it has one, and that of course then crashes my agent. In other words, if I didn't add this X and Y coordinate and make this skill intuitive for the LLM, it would never work, because I cannot force the LLM to not hallucinate, but I cannot make the skills in such a way that it cannot really hallucinate because it's more intuitive for the LLM. This is tricky to do. It's usually something that you notice as you implement the skills for the LLM. So this was roughly everything that we needed for NetPlay. And now let's look at an example of what the LLM can actually do and what it can't do. And for this, I have created a bunch of scenarios to test what the LLM can do. And the original task that I gave it was to drop a plate mail and an iron ball in a room containing the statue. So we have an iron ball, which is a blue dot. We have a plate mail, which is this white thing. And we have a statue, which is for some reason a dummy, a wooden dummy. And this is a very vague task. It's not very easy to understand what should the LLM actually do. So I also have another example and where I give it more tips, such as the 2 items that I'm asking it to carry are very heavy. If you carry them both, it's very likely you're going to get overburdened and you're going to get very slow. The moment a monster finds you, it's probably going to get a lot of attacks on you. So please only pick up one at a time. Also make sure that the moment you encounter monsters, defeat them immediately, because you're carrying heavy items. So it's going to be very tricky to fight, to try outrun those monsters. And finally, it might be easier to just teleport yourself using some kind of teleportation wand than actually, god damn it, I'm sorry. Just ignore that. To use a teleportation wand to teleport yourself instead of having to walk yourself. So let's look at an example where I actually ask the language model to play without tips, and it's going to go over in a blink of an eye. So don't be discouraged if you don't see what happens. I'm just going to tell you what happens. So the LLM just picks up the items that it has to pick up, and it drops them immediately, and then it says, I'm done. But the problem is, the room it's in, there's no actual statue. So it just decided, I have no idea where a statue is. I'm going to pick up the items, drop them, and then I'm done. It didn't fully understand what I told it to do, because I didn't give it enough tips. Essentially, the task I gave it was very vague, and the LLM didn't fully understand what to do, so it just did something and then decided it was done. Now, with the tips that I've given it, it actually performs much better, where it first decides, okay, I'm first going to pick up the heavy plate mail, and then it's going to pick up the teleportation wand. And what it's going to do, because I told it you can use the teleportation wand to teleport, it's going to teleport. And this is where the statue actually is. So it drops the item, and then it decides to, okay, I've dropped the item, I'm going to teleport back. Sadly, now it's in a room with monsters. So it's going to kill the monsters, because I told it, kill monsters the moment you encounter them. And finally, it teleports again to get to the first room, and it picks up the second item, which is the chain ball. Now, it could have decided to teleport again, but in this case, it just decided to explore the level eventually, which we should see soon. Yeah, so now we can see that it's now exploring the level. to figure out how to actually get to the final room without teleporting. And eventually the explore level skill actually finds the final room. Of course, our explore level skill is very general and it keeps exploring until it eventually times out. So we have to wait a little bit until the explore level skill actually times out, which is not the most efficient way to play the game. But again, this is kind of a balance between skills and high-level planning for LLMs. But of course, once the skill actually times out, the LLM then decides to go to the final room and actually drop the final item that it wants to drop there. And then it does some more random things because it doesn't tell me yet it's done. It's just going through the plate mail again, picks it up and drops it again, probably because it forgot that it actually did that before. And now it told me it's done. So it works much better than if I don't give it tips. Which brings us to, when should we actually use large language model agents? And what we've just analyzed is, what does this mean for us as like game developers? What tips and tricks can we use to make this actually work? So there are a lot of pros with large language model agents, but also a lot of cons. And the most important thing about large language models is they're extremely easy to configure. Once you set them up, you can ask them to do a wide range of tasks, which is something that's usually not possible with any other technique that exists at the time. Yeah, they can perform many tasks and they can then easily adapt to game changes, given that the skills that we provide to the LLM actually adapt to the game and themselves, right? But usually as game developers, you have to have some side of skill set, right? Pathfinding has to work all the time for the game, so we can probably give access to the LLM easily without breaking anything as the game evolves. And LLMs can handle edge cases for us, so it makes it a lot easier for us to develop agents because we don't have to think about all the edge cases. Now, this technology is extremely new, and LLMs have a lot of issues. So it's very likely this technology is not ripe enough to actually be used in production yet, which should change in the future. We're going to look at that soon, but that is something to keep in mind. Of course, LLMs still have a lot of issues, and they're still very expensive. Yeah, we require observation descriptions, which are a huge burden. We have to describe the game somehow to the LLM, unless we have multimodal LLMs, but that's, again, very tricky. And we have to have the skills, which I feel like is the least of our concerns, because usually we have some kind of skill set that we can use to give to the LLM. And of course, we have the issues that LLMs have in general, like they're slow, expensive, and they cannot really think outside of the box, as we've seen. They just do what you tell them. And if it's a vague task, you have to be very descriptive of what happens. So where do we want to use LLMs? Given what we just looked at, there are a lot of criteria that we have to consider, right? The observations should be easy to describe, so we don't have to do a lot of work. The task should be straightforward, again, right? The task should be just step, 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 and not a lot of thinking done by the LLM. It just knows this is what I have to do, and I can roughly do them step by step. And because we want to do playtesting, the solutions that we try to the LLM to find should be easy to verify. We've seen before that the LLM can tell us when it's done, but it's not 100% perfect, so it might make mistakes. So in the best case, if we want to use it for playtesting, we want to still implement the test ourselves. Let's look at some games. So let's look at a racing game. Should we use LLMs for a racing game? Very likely this is not a good idea, because racing games require a lot of manual movement, a lot of low-level decision-making, where it's very tricky to high-level planning on what you're going to do in the long term. So these are usually not the best places where you can use large language models. Puzzle games might be more interesting, but we have to consider what we are using it for. If we want to verify if a puzzle solution can be solved, right? We have a solution for a puzzle, and we want just to check, does this solution still work? This is a good case, compared to if we want the LLM to figure out itself on how to solve a puzzle. It might be able to do that, but it's very likely that it's going to get stuck because it's very uncreative on how to approach puzzles, which puzzles require you to think creatively. Menus, those are probably very well suited. They're easy to describe. They're easy to navigate for large language models, at least depending on how difficult the menus are. And they are mostly text, so they're easy to describe. I think I just repeat myself, but they're relatively easy to handle for large language models, so they might be a very good use case. And of course, grid-based games are probably easier than very complex 3D games, where it's very difficult to describe what is going on in the world. And a lot of RPG mechanics are mostly menu-based, So again, they might be very well suited for testing with large language models. And how can we use them? So let's look at an example that I think might be very well suited. Let's say our developer updates our game, and we have our continuous integration that just tries to now, test our game, do a lot of builds, whatever. And we want to do some kind of regression tests where we have a lot of components, such as we create some kind of isolated game scenario that we want to test, right? It's very simple, not too complex, so our LLM can actually test this game scenario. Then we have our agent, which we give the task that we want to test. And finally, it plays the game. Now, sadly, right, we still have to do some more manual work, which is to actually verify if whatever we were trying to test was actually achieved. So we have to manually implement some kind of task verifier, which should be very easy to do, such as in this case, we can just check, is the chest actually open? Then the task was probably accomplished. So it's much easier than actually having to implement the agent ourselves. And finally, of course, our developer receives some kind of feedback so they can keep updating the game. Okay, so this was roughly the talk. Let's look a little bit at the future. Now, I'm pretty confident that LLMs will get faster and cheaper in the future, such that this technique that I've just presented will get much more easier to implement and much cheaper to run. Of course, a big hope is, and a lot of research is going into multimodal LLMs that can not only understand text, but also images, audio, and of course, I'm also working on, and a lot of other people are working on, integrating LLMs more deeply into games so they better understand how to play games than just you describe the game to the LLM. And finally, dynamic context. We've seen that LLMs work best if you describe in a very good high detail on how to play the game. So it would be nice if we can just say, given the current situation that you're in, we're just going to inject whatever you need to know on how to play well into your prompt so it can automatically play the game in a very good manner. And this is called retrieval augmented generation. Now, it doesn't work yet very well for games. It's mostly for text prompts. But of course, again, research is going into how we can do this for other scenarios. So here are all the sources which you might want to take a picture of. I'm not sure if you're interested in that. Otherwise, you can, of course, later contact me if you want the slides for yourself. And if you want to get in touch with me, this is my email address, my LinkedIn. And if you want to know more about NetPlay, I have my GitHub repository over here, which is where I have a blog post. And my paper was also published currently on Archive, but it's also available at the Conference on Games 2024, where I have it published. So it will soon be available there as well. And make sure that you rate my talk after using the mail that is being sent to you. And thank you very much for your attention. So, any questions?
Hi, very interesting. Is it on? Can you hear me? Yep. Okay. Let's say you're developing a new game. You haven't gone to market yet. You're still in early design. Is there anything you can do in designing your game to make it easier to be tested by LLM so that it's kind of sort of ready for testing by bots?
So essentially, you're asking if you're designing a game from scratch, right? How to make it easier to test the game in a very early state, or?
Yeah, I mean, you could, obviously games go through many iterations. Yes, you've got CI, which is, you're doing some unit testing, etc. But you want to have maybe a full regression test suite, which you update as you go along, and you don't want it to be sort of a finely detailed at a code level because that gets extremely expensive to maintain. But you want it to be like a generic thing. So, is there a mechanism you can build into your games to make it much more LLM friendly?
So to make the game more LLM friendly, so you're asking about how to make the game such that it's more friendly for LLMs.
Yeah.
I feel like the best way would be to keep in mind in the first place on how to create observation descriptions, because at the moment the biggest hurdle is to actually describe the game to the LLM, and there's a lot of complexity on how to actually describe the game. So if you essentially keep this in mind in the early future, where we have to describe it somehow to the LLM, and we need to generate these descriptions dynamically, that's the most important thing that I think has to be considered.
Thank you.
So, how do you actually make the LLM aware of the skills it has available to use to play the game?
So the skills again are simply functions that I've implemented. So I've just described every function using some key piece of text that tells it what it does, right? So it has the name of the function, right? Move to, a description moves you to this position, and then it gets access to the parameters, such as in this case, you have an x coordinate and y coordinate as parameters. I don't describe the parameters what they do themselves because the LLM can usually infer it itself if they're intuitively described. But essentially, it just has a very big list of, yeah, these are all the skills you have available. Pick them, pick whichever you want. There's a big concern that there is, if you give them a lot of skills, it's very likely that the LLM is probably ignore most of them until it's somehow randomly decides to use them. They are still very hyper focused on the task at hand. So if you ask them to move somewhere, they're probably mostly going to select your move to skill. But that again, we can remedy by giving it more instructions.
Okay, so my question have to do with you made mention of RAG, and do you think in the near future it will be very possible to implement this RAG in games? Because
So essentially implementing RAG for games, like currently RAG only exists for like text-based prompts, where we then can dynamically find content that's relevant for the prompts. Now to plug myself in here, I'm trying to look into more like how can we actually figure out, given a game situation, which situations are maybe similar, so we can actually do RAG. But of course, again, there's a lot of research going into that. How can we actually apply LLMs better to games? And I feel like this is going to be more relevant in the future, but I cannot say if it's going to happen soon or if it's going to take a long time. It's very difficult to predict.
So when you have a grid, you have rather large changes in state when you move from square to square. In a video game, you have really rather small changes from frame to frame. So can you just talk about how your ideas might work in that real-time kind of context?
Now, because we use skills that take care of a lot of low-level planning, the large language model actually hasn't taken into account like all these small changes as we play the game. If there are like small changes between frames, they are going to be taken care of by skills, right? The LLM just decides I'm going to select the skill here, and then the skill is going to run until it's done over here, and then the LLM can make the next decision. So that not only reduces the amount of LLM calls we actually have to make, but also is much better suited for LLMs because it can do the high-level planning and not try to move an arm pixel by like frame by frame, which is very expensive and not very well suited for them.
Any more? This is going to be the last question.
Quick question. Are you mapping phrases to the skills? Like move to is mapped to the move to function?
Let me
Or
quickly.
can you say bring yourself to the fountain and it'll work just as well?
Could you repeat the question because I didn't get it quite? So essentially what I'm showing here is right, I have the skills, it tells you what the skill does, and then it has the parameters. So this is everything the LLM gets access to.
Oh, okay. I was just trying to understand the English phrase. You know, if you wanted to build LLM from scratch, what prompt does it know matches to the
So
function? Yeah.
I'm using pre-built LLMs, so GPT-4, Llama 3. I'm not using any trained LLMs, like I'm not training any myself.
Oh, okay, okay. Thank you.
So it's getting fine-tuning.
Yeah, so yeah, essentially all this work I've just shown was without fine-tuning. This was literally just LLMs that exist without any fine-tuning, and they work perfectly well. Of course, fine-tuning could, of course, improve them much more. But then the question is, how do you tune them for games? It's, yeah. Yeah, that's, I cannot answer that because it's, again, very difficult how to get the data to fine-tune it. Again, research is going into that. So I sadly cannot tell you that. The problem is I think we have to talk afterwards because I think we have to stop.
Yeah, you can. Yeah. we have
So
to
you
wrap
can
up.
come over here and then we can talk more. Yeah.